So we're going to start talking about how we can do solve torque problems, and these are pretty general torque problems, but the process is the same for all of them. Just a couple things that you need to pay attention to. The way that we did it when we did Newton's second law problems is really the same exact way. We just now, instead of doing F's, we have RFs. Okay. Other than that, it's essentially the same thing, and we have to pay attention to what our perpendiculars are as well, and that'll come into more effect later on. So, excuse me. We've got, the first problem says, two paramedics rush a 60-kilogram man from the scene of an accident to the ambulance. They carry him on a uniform 30-kilogram stretcher held by the ends. The stretcher is 2.6 meters long, and the man's center of mass is 1 meter from the first paramedic. How much force must each paramedic exert to keep the man horizontal? All right, these questions, we're going to draw essentially like a modified free body diagram. All right, I wouldn't necessarily call it a free body diagram, but it's kind of similar.
Wait, you mean that we're not drawing the actual scene?
No, we're not drawing the actual crash, and that's what we're going to do, essentially, for the most part. So we're going to draw, if we had a free body diagram, right, we would just pick, if it was a free body diagram, it would be something like this, where we have all the forces acting on one object, right? And that's what we would do. But in this, it's just really more of a picture to show the forces that are acting on it, but you also want to put in the distances or the radius for each torque as well, okay? So the first thing we want to do is let's draw the forces on there. So we know that we have a paramedic on each scene, and they're held on each end. So we have a force from paramedic 1, and we have a force from paramedic 2. Okay? We then have, they say it's a uniform stretcher. So the center of mass is going to be right in the middle. And we'll call that W sub S for the weight of the stretcher. We're talking about the stretcher. Okay? Now, the next thing, and we kind of skipped ahead, what you really want to do before you even put forces in is you want to pick a point with which things are going to rotate, right? An axis of rotation. You have, unless they specifically tell you, you can put the axis of rotation wherever you want. Okay? So unless they specifically tell you, you can put it wherever you would like. Some questions they'll say it's a seesaw and the fulcrum is right in the middle. Or, I'm going to tell you. Another problem may be it's pinned on the end. Those are your axis of rotation. If they don't tell you, the best thing to do is to put it on an unknown force. Okay? So in this case, we don't know F1 and we don't know F2. All right? So I would suggest you put it on F1. You can put it on F2, that's fine. But you want to put it on something you don't know, and you'll see why in a few minutes, why you want to put it on something that is unknown. All right?
Is it kind of like the truss bridges?
Kind of.
Like where the reaction forces go?
Kind of. So now that we know where the center of rotation is, right? We can say then that the weight of the man is 1 meter from that side. Okay? So now that we have these things in here, we can draw our distances. We are 1 meter away from the axis of rotation. Okay? Whether they say 1 meter from the first paramedic, so we can do that as well. Yeah, put it right there. So now we know that if this is our axis of rotation, this is 1 meter. Right? Say it's 1 meter from the man, so we got it there. If the stretcher is 2.6 meters long, then obviously this is not drawn to scale. The center of mass of the stretcher is now 0.3 from the man, or 1.3 from the other end. from the first paramedic. And then the last guy we have is F2. And this is 1.3 meters as well. Okay, make sense? Are we okay with the drawing? The drawing is the important part, all right? That's the important piece to getting this, is making sure that we have the drawing good to go. All right? So they're carrying him. Is it rotating? Is it spinning? No, okay. So what we can say then is that the sum of the torques, which is equal to I alpha, but because we're not rotating, alpha is equal to 0. So that whole side is equal to 0. Now again, remember, this is the rotational version of Newton's second law. And instead of F equals ma, we get the sum of the torques is equal to I alpha. So what we're going to do, and just as a reminder, remember, anything that flows or rotates counterclockwise is going to be positive. So what we'll do is now we're just going to write the torques in there. All right? We have a torque from the second paramedic. We have a torque from the stretcher. We have a torque from the man. And we have a torque from the first paramedic. And they're all equal to, the sum of them is equal to 0. Yep.
Wait, I thought
I haven't done anything yet with signs. I'm just picking counterclockwise to be positive. Okay?
I thought stretchers are on wheels. Why do they have to do that? Why are they carrying?
All right, so if I look at this, F2 is going to cause it to rotate in the positive direction, correct? So I'm going to leave the torque 2 as positive. The torque, because of the weight of the stretcher, is going to cause it to go clockwise, which is negative. The weight of the man, the torque because of the weight of the man, will also cause it to go in the negative direction. So that gets a negative sign. And then, what direction would F1 cause it to rotate? It wouldn't, right? Let me just put a plus in there just to make it mathematically consistent. Okay? So if we look at T2, right, torque 2, it's force times radius. So we know that he applies a force of 2, of F sub 2, and it's a distance of 2.6 meters away.
Wait, isn't your center of balance?
My axis of rotation is right here,
Oh, okay.
which is 2.6 away. Okay. The weight of the man, the force of the stretcher, is going to be equal to the mass of the stretcher times g. And then the stretcher is 1.3 away. That's your R. The man, it's going to be the mass of the man times g to find his weight. And then he is 1 meter away. And then the last one, we have the force of the first paramedic. And his radius is 0. Right? Because his force is directly on the pivot point. Here's why it's important that you put the pivot point on one of the unknowns. If we didn't have it right there, we'd have one equation with 2 unknowns. Okay? You'll see how we can reconcile that, but this just makes life a lot easier by putting the pivot point on one of the unknown forces. It automatically cancels it out. Okay? No. Kind of. We're not going to go back here and do it. We're going to go to another equation and do it. Okay? All right, so we have 2.6 F2. Now, mg, the mass of the stretcher, is 30. So 30 times 10, so we got 300 times 1.3. And then the man is 60 times 10, and then times 1, and that's all equal to 0. Okay. So 2.6 F2 is equal to, what is 300 times 1.3? 390. All right, so 390. So that's 990, right? I can math. So if we divide by 2.6, how much force does a second paramedic have to offer? Yeah, 990.
380.6.
We'll call it 381 newtons. So the second paramedic, the guy on this side, has to provide 381 newtons of force. Okay? So now we need to find out what F1 is, correct? We need to find out how much does the first paramedic need to apply. So we can't go back to the torques. I mean, we can, and we can move the pivot point, and we can solve for F1. That's too much work. There's a faster way. Okay? Instead of going back and looking at the sum of the torques, we can look at the sum of the forces instead. All right? And if we look at the sum of the forces for that part, again, it's not accelerating. Right? We're looking, all the force is being applied in the y direction, so and it's the stretcher's not going up or down as they do that, okay? So if we look at our picture, just in terms of the forces, we have F1, we have the weight of the man, the weight of the stretcher, and we have F2. Stop that, will you? And they're all equal to 0. F1's going up, so we give it a positive. The weight of the man is down, so it's negative. The weight of the stretcher is down, so it's negative. And F2 is up, so it's positive. So we get F1 minus the man, which is 60 times 10, right, mg, minus the weight of the stretcher was 30 times 10, plus 381, and that's equal to 0. All right, so we've got, what does F1 come out to be? We've got 600, 900, what's that? 519. So the first paramedic has to supply 519 newtons of force.
Why does that one gotta do all the work?
So my next question was, why does F1 have to supply more force than F2? Right, more weight is directed or is on his side, right? So he has to carry more, he has to do more of the work, he has to carry more because more of it is closer to him. The man is closer to him. Okay?